Ever wonder what gives a lemon that sour punch? Or why soap feels so slippery in your hands? Well, the answer is all about one of the most fundamental ideas in chemistry: acids, bases, and salts. Now I know, that might sound like a super tricky chapter from your old textbook, but we're about to show you how this science is happening all around you every single day.
I love this quote because it's exactly what we're going to do. We're going to pull back the curtain on the chemistry that's hiding in plain sight. You know, in the food you eat, the products you use. By the end of this, you'll see it's not magic at all, just a really fascinating set of rules that governs our world. So here's our game plan. First, we'll meet our main players, acids and bases. Then, we'll put on our detective hats and learn how to identify them. After that, we'll check out what happens when they mix, figure out how to measure their power, and finally, we'll dive into the surprisingly diverse world of salts. Let's get right into it. All right, let's jump in. At the heart of this whole thing are two types of chemicals with totally opposite personalities: acids and bases. If you can get a handle on these two, everything else we cover is going to click into place.
So what's actually happening on a molecular level? Well, an acid is basically a proton donor. The moment you put it in water, it just gives away a positively charged hydrogen ion, that H+. Just think of it as the chemical that's always trying to give something away. And that one simple act is what gives acids all their unique properties.
This table is basically your cheat sheet for telling these two apart. On the left, you've got acids, with that classic sour taste and their habit of donating H+ ions. And on the right, you've got bases. They're complete opposites. They're bitter, they feel slippery, and they donate hydroxide ions. But for a chemist, the most important difference is that last row, how they mess with litmus paper. They give you opposite colors, which is a super simple visual test.
Okay, here's a great little memory trick for you. Acids can be dangerous, right? And what's the universal color for danger? Red. So just think, acid, danger, red. It turns blue litmus paper red. See? Simple as that.
You know, acids are literally everywhere in our food. And here are a couple of handy little phrases to remember them. Very acidic orange city links vinegar to acetic acid and oranges to citric acid. That's what makes citrus so tart. Then you've got TT tomorrow, which connects tamarind to tartaric acid and tomatoes to oxalic acid. All of these are what we call weak organic acids, and they're totally safe to eat.
Okay, so obviously we can't go around a lab tasting chemicals to see if they're sour or bitter. That is a terrible idea. So how do chemists tell them apart safely? Well, they use these special substances called indicators. Indicators are basically chemical chameleons. They're substances that change their appearance, usually their color, but sometimes even their smell, to signal whether they're in an acidic or a basic environment. They give us a clear visual clue. No danger involved.
This chart is so cool because it shows some of the most common ones. We've already talked about litmus, but check out turmeric or haldi. It turns red in a base. If you've ever spilled curry on a shirt and tried to clean it with soap, which is a base, you have done this exact experiment. Even better is phenolphthalein. It stays colorless in an acid, but turns this amazing vibrant pink in a base. Super useful in the lab. And get this, it's not always about what you can see. Some indicators, called olfactory indicators, use our sense of smell. The very distinct smells of onion, vanilla, or clove oil will just vanish when you add a base. It's a pretty neat trick. All right, so we know what they are, we know how to spot them. Now for the exciting part. What happens when acids and bases actually meet other chemicals? This is where all the action is. This chart is absolutely crucial because it reveals these predictable patterns. If you react an acid with a metal, you always get hydrogen gas, and you can prove it with that classic pop sound test. React it with something like baking soda, a metal carbonate, and you get carbon dioxide. But that last one, that is the most important reaction of them all. When an acid and a base meet, they completely cancel each other out in a process called neutralization. All you're left with is salt and water. And here is a fantastic shortcut for you. If you see a compound that's a metal plus oxygen, a metal oxide, it's almost certainly going to act like a base. If you see a nonmetal with oxygen, it's probably going to act like an acid. That is super useful to keep in your back pocket.
So here's a really important point. Not all acids or bases are the same. Some are way stronger than others. And to measure that strength, we use something called the pH scale.
The pH scale just gives us a simple number, from 0 to 14, to measure strength. 7, right in the middle, is perfectly neutral, like pure water. Anything below 7 is acidic, and anything above is basic. But here's the secret. The scale is logarithmic.
That means a pH of 1 is 10 times more acidic than a pH of 2, and 100 times more acidic than a pH of 3. So tiny changes in the number mean huge changes in strength. And trust me, this scale is incredibly important in our daily lives. That super acidic environment in your stomach, it's essential for digestion. The pH of soil literally determines if crops will grow. Even something like tooth decay is a pH problem. It kicks in when the acid in your mouth makes the pH drop below 5.5.
Okay, let's connect the dots here. We know that eating sugary stuff makes your mouth acidic, which can lead to cavities. And we all know we're supposed to brush our teeth to stop that from happening. So what's the actual chemistry behind why toothpaste works?
It's simple neutralization. Toothpaste is basic, or alkaline, so it reacts with the acid that's in your mouth and cancels it out, bringing the pH level right back up above that dangerous 5.5 level and protecting your teeth. You are literally doing a chemistry experiment every single time you brush.
That whole idea of neutralization leads us perfectly into our final topic, salts. Now, when we hear the word salt, we immediately think of table salt, right? But in chemistry, it's a way bigger category of compounds.
In chemistry, a salt is simply the ionic compound you get when an acid and a base react. They neutralize each other, and the salt is what's left over, along with some water. The most famous example, of course, is hydrochloric acid and sodium hydroxide reacting to create sodium chloride. Yep, our everyday table salt.
Okay, this is where things get really cool. Starting with nothing more than table salt and water, a brine solution. A process called the chlor-alkali process zaps it with electricity to create 3 totally new and incredibly valuable industrial chemicals. It's a perfect example of how we turn simple stuff into the building blocks of our modern world.
And those 3 products are absolutely everywhere. We get hydrogen gas, which is used for fuel and making fertilizers. We get chlorine gas, which is vital for purifying our water and making plastics like PVC. And we get sodium hydroxide, a strong base used to make soap, paper, textiles, the list goes on. All of that from simple salt water and electricity.
So we'll leave you with a little challenge. Now that you've got the fundamentals down, you're going to start seeing this chemistry everywhere. Think about it. Why does baking soda, a base, help soothe an acidic stomach? Why do gardeners add lime, another base, to acidic soil? The answers aren't a mystery anymore. You now have the scientific toolkit to see the world in a whole new, amazing way.